This is part of a series on data structures. In this video, I want to talk about variables, data types, and arrays. Some people might find this unnecessary detail, but lots of us really need to see what's under the hood to understand what's going on and why. So take what you need. So say I've got this sentence. The quick brown fox jumped over the lazy dog. It's got one of each English letter. So what does it look like on a computer? This is what it looks like in a hex editor. A hex editor is a way of looking at data in memory. So this tells us that the character capital T is represented under the hood by 5-4. But what does that mean? Check out lowercase o. It's 6F. These aren't the numbers we're used to. This representation is hexadecimal, hence the name hex editor. But what does that mean? Let's start with switches. A computer's memory is basically a giant bank of switches. Switches can be on or off, 0 or 1. So let's look at hands. Not the best drawing ever, but bear with me. When we're kids, we usually learn to count on our fingers. We can represent 10 digits on our fingers. We call this the decimal system. Decimal is based on 10. It's also called base 10. When we're counting in decimal, when we run out of numbers, we just add another digit. We roll over from 9 to 10, 1, 0. And every time we run out of numbers, we just tack another digit on front. 100, 1,000. The decimal system is just a side effect of our 10-fingered biology. Computers are based on switches, so they don't have 10. They have 2. Binary, 0, 1. But binary numbers work exactly the same way. When you run out of digits, you stick a 1 in front and keep going. 1, 0, 1, 1, 1, 0, 0, and so on. In decimal, every time we tack another digit on front of the number, the magnitude goes up by 10, because it's a 10-based system. 10 times 1 is 10. 10 times 10 is 100. 10 times 100 is 1,000, and so on. The same thing happens in binary, except it's based on 2. 2 times 1 is 2. 2 times 2 is 4, 2 times 4 is 8, 2 times 8 is 16, and so on. This is fine for computers. It's based on their physicality, and if we thought they had feelings, this probably wouldn't stress them out any more than base 10 numbers stress out people. But for people, when base 2 numbers get big, it's uncomfortable. It really sucks to say 0, 1, 1, 0, 1, 1, 1, 1. It's cognitively hard. 5-7 is easier. Hexadecimal is our solution to this cognitive problem. We use letters A through F to represent the 6 digits after 9. So it's 9, A, B, C, D, E. A is 10, B is 11, F is 15. Then when we get to 16, we add another digit. And just like anything else, we stick a 1 on the end and roll over to 0. 1, 0 is 16. This lets us represent 4 binary numbers in a single hexadecimal digit. You see this a lot in computing, in everything from hex editors to web color codes. So a bit is a single binary 1 or 0. 8 bits, which corresponds to 2 hexadecimal digits, is called a byte. And a word is whatever the processor wants. This is based on hardware. It's usually going to be a power of 2, but it changes. It used to be that most home computers had 16-bit processors. Then they switched to 32 bits. In the last few years, most systems have switched over to 64 bits. Give it some time and eventually they'll have us switching over to 128 bits. So let's look at our hex editor again. All these numbers on the left represent the memory location, or address. Every single piece of memory on the computer has an address. It's usually a much higher number than this, often with an X in it, because you've got multiple gigabytes of memory and you need very large numbers. So if you've done much programming, you've probably used variables. It's where you give a label to data. But what does it look like under the hood? A variable has 2 pieces. It has a data type, so the program knows how many bytes of memory to look at and how to translate the 1s and 0s into something meaningful, and something that points to the memory location or address that holds the data. There are lots of different data types. These are probably the most common. Character, usually abbreviated char or chur, which is something like the letter A. It could be anything you'd type. It could even be a numeral, but if you've got 5 represented as a character, it's more for typesetting. You can't do math with it. If you want to do math, there are a bunch of different ways of representing numbers. Here's the most common. Integer, which is abbreviated int, is something like 97. Importantly, these only have a certain number of bytes allocated to them. If you get to the point where you'd wrap around and add a new digit, but there's no space left, you've reached what we call max int. Depending on how you're programming, you'll either wrap around to the minimum integer, going from a giant number to the tiniest number possible, or you'll hit a wall. Usually this doesn't come up, but it's worth being aware of if you're dealing with giant numbers. And floating point numbers, or floats, are how most decimals are represented. Numbers like 0.0059241. Floating points work like scientific notation. The decimal can float around anywhere. Theoretically, there's an upper bound for how big a float can be, but usually you just lose precision and drop numbers off the end of your decimal. An array is a chunk of memory that contains a bunch of the same data. For instance, my sentence is an array of numbers called a string. They're all characters. You can access any item in an array by putting square brackets after the variable name with an index inside. The index is how many items into the array it is. My sentence with an index of 0 is capital T. With an index of 1, it's lowercase h. An index of 8 would give it the letter K, and remember it's hexadecimal, so this label 10 would be an index of 16 for F. This should give you a sense of what's under the hood with most of your data. Most data structures are built on some combination of single unit data types, arrays, and the way variables can point to addresses in memory. Arrays are great for lots of applications, but they aren't perfect. Most data structures that manage groups of data have been created to either be like arrays but better, or to do the kinds of things with data that arrays aren't great at. We'll talk about some other data structures in the other videos in this series.